And the last section, we started with ionic bonding, then we moved to covalent bonding. And historically, we moved through the understanding of covalent bonding through its stages. And we're at the point now where we're in the localized electron model, which is part of the valence bond theory. Localized electron model, and then the VSEPR, valence shell electron pair repulsion model, to determine the geometry of the molecules. And that works pretty well. But there's always a but. When we try to predict, we can get the shape of the molecule, methane, like that, fairly reliably. All we have to do is draw the Lewis structure. We have 4 valence electrons here, and 4 times 1 is 4. So we have 8 electrons. So if we draw carbon in the middle and then put hydrogens all around it, like that, right? It's got 4 groups, and groups when we have 2, 3, 4, 5, and 6. 4 groups, the electronic geometry for 2 groups is linear. This is a refresher. This is trigonal planar. This is tetrahedral. So that's what this one is. Tetrahedral. And that's confirmed from laboratory experiments. This one is trigonal bipyramid, and this is octahedral. Okay, this is by way of the VSEPR. Okay, let's see, we've already done that and that, so now we're on to this. Okay, here's the problem. With the localized electron model, we're saying that the electrons belong to each of the atoms, and the only way bonds form is by sharing, overlapping orbitals. If we try to do that with carbon, hydrogen is no problem. Right? Hydrogen is 1s1. That's it. It can't be anything else. But carbon has 6 electrons. It's 1s2, 2s2, 2p2. There's the problem. It has 2 electrons in spherical orbitals and 2 electrons in the p orbitals. Right? So if we overlap these s's with those s's, you get a different geometry than you would with overlapping the p orbitals. Right? They're not all equivalent. That's what we need. In order to have a tetrahedral structure, we need equivalent orbitals to bond with each one of the hydrogens. Okay? The shape of the molecule is tetrahedral, and the bond angles are 109.5 degrees. All right, that's confirmed. All right, so here's the situation. We have a localized electron model from the valence shell, the valence shell theory. So what do we do with it? You know, remember you have 3 choices. You can restrict its use. You can modify it. You can throw it out and start over. We're not ready to do that yet, not historically speaking. Or the 4th one is you can make a religion out of it. So we're not going to do that. So, all right, I told you that already. S2 and P2 orbitals are the overlapping valence shells. Right? We can't get a tetrahedral out of that. So the answer is hybridization. We hybridize these 2 orbitals with those 2 orbitals, and we produce no, P's have three, right? 1, 2, 3. These have one. So we overlap these three with that one, and we get a hybrid orbital. And the hybrid orbital is called sp3. How many of those do we get? You get the same number of these as the ones that went in. So we have 1, 2, 3, 4. We have 4 of these available now, and they're equivalent. Those hybridized orbitals give us this tetrahedral structure. Okay, so let's expand our table here. Hybridization. So this one is the one we're talking about. It will always be sp3 to produce the tetrahedral structure, the hybrid orbitals. All right. This was proposed in the 30s by Linus Pauling. Remember, Linus Pauling was the one who wrote that book on the nature of the chemical bond and got a Nobel Prize for it. And so when he proposed this theory, there was not much resistance to it because it solved the problem, for one thing. So the theory was modified to accommodate reality. Okay. Now, he didn't just pull this out of thin air, right? He was well-versed and competent in quantum mechanical equations, like originally proposed by Erwin Schrödinger for electronic structure of individual atoms. Then those equations were expanded to cover molecules and then modified further to accommodate hybridization. So there's a mathematical background for all of these modifications. Okay, so this hybridization, sp3 hybridization, always gives you a tetrahedral structure. That's the nice thing about it. When we modified this hybrid, you've got 4 orbitals here. That's like 4 groups, gives you tetrahedral electronic structure. All right. Now, when we look at the energy, that's one of the problems with the valence bond theory, is that it doesn't accurately predict energies, actual values for energies. It gives you sort of a fuzzy feeling, yeah, it's up here or down here. And that's what we're trying to show here. When we hybridize the s orbitals with the p orbitals are a little bit higher in energy than the s orbitals because the s orbitals have that penetration effect. All right, so they're lower in energy. And when we hybridize all 3 of them, you get 3 P's versus 1 S. So the energy level of the new sp3 hybrid orbitals are about 75% from the S's to the P's, right? Because 3 divided by 4 is 75%. And the quantum mechanical equations predict this shape for the molecules. So we put those on the left together, hybridize them, and now we get 4 equivalents pointing to the apexes of the tetrahedron. All right, there's a bigger view. And we don't have to hybridize the hydrogens. We just overlap those hybridized orbitals on the carbon with the 1s orbitals on the hydrogen, and we get a bond. A single bond for each one. Now let's look at another possibility. Ammonia. So here we have ammonia. Okay. We draw the Lewis structure. Nitrogen has 5. 3 of these makes 8. So we have, 3 equals 8 electrons. Okay. So with nitrogen in the middle, and then we have a hydrogen in the back, a hydrogen over here, like that, and these like a triangle on the bottom, and then we have these two up here. How many groups do we have? 1, 2, 3, 4. So electronically speaking, this is also tetrahedral. Molecular geometry is going to be a triangular pyramid. But the hybridization is based upon the electronic geometry. So for methane and ammonia, you're going to have sp3 hybridization. What that means is this is an sp3 orbital, this is an sp3, this is an sp3. All those. And this is an sp3 with a lone pair in it. Now, the bond angle is still going to be less than 109.5 because remember, these lone pairs, they're not confined by a bond, so they tend to go balloon out, and they put pressure on these guys. So they shrink down to, 108, something like that, or maybe less. So the point here is that you don't have to include only bonded groups in order to determine this hybridization. In this case, we had one lone pair that went into the hybridization. Okay. Those are just steps that you take. All right. You still have to follow the VSEPR and draw the structure, find out how many groups you have around the central atom, and then decide what its shape is, and that will give you the hybridization required. All right, so there's what it looks like for ammonia. How about C2H4, ethylene? Now, ethylene is going to have two centers of symmetry. It has two carbons, and each carbon will have its own symmetry. So C2H4 gives us what? Well, let's see, 2 times 4 is 8, plus 4 is 12, right? 12 electrons. So we have carbons bound to carbons. Remember when we draw these like that, this is organic chemistry. Those two carbons are bound together, and then the hydrogens go symmetrically, like this. 2, 4, 6, 8, 10. Right? There's no room for electrons on the hydrogens, so we put those extra 2 on one of the carbons, but we need to make an octet, just like always. So we take these 2 and make a double bond here. That gives us 2, 4, 6, 8, 2, 4, 6, 8. So that would be the Lewis structure for ethylene. Now we can determine the symmetry around the carbons. 1, 2, 3, 1, 2, 3. So it's the same for both of them. We have 3 groups, right? It's trigonal planar. Around this one and trigonal planar around that one. Trigonal planar means you only need 3 hybridized orbitals, right? So that means sp2. We're only going to use 2 of the p's with an s to make the symmetrical trigonal planar hybrids. That means we have a p left over that wasn't used. So it's like saying, okay, the sp2s are like that, like that, like that. And then we have this extra p sticking out here. Actually, both of them have extra p's, right? So what are they good for? They're good for making that pi bond, that second bond in it. They overlap to make the pi bond. The pi bond is made by side overlapping p orbitals that were not used in the hybridization. Okay, bond angles, of course, are going to be 120 degrees, like always, trigonal planar. There's the molecule. Can't be sp3 because it's not tetrahedral. It's trigonal planar. There you go. Have we talked about sigma? We've talked about sigma and pi bonds, haven't we? Okay, well, I'll talk about them again. A single bond, whenever you've got two atoms bonded together, there's always at least a sigma bond. Then if you have a double bond, any extra double bonds, one or two usually, they're called pi bonds. Sigma bonds are on axis for their electron density and sharing orbitals. Pi bonds are off axis overlaps. So they can be like this or like this. Okay. So dinitrogen would have a triple bond, which means one sigma and two pi's. So in this case, we have a sigma here and a pi. All right. Oh, that's coming up. I should have looked at my slides. There you go. Pi bonds are always formed from sideways overlapping p orbitals. Let's see. Now, how about the energies? Well, you've got two p's orbitals. One of them is left over. So it's at the same energy as the original p orbitals. But when you hybridize two of those p's with an s, you only get 2/3 character for the p orbitals and 1/3 character for the s. So the energy is going to be lower for those hybrid orbitals. Right? Instead of 75% of the distance, it's only 2/3 of the distance related to energy. And that's what it would look like. You got the sp2 hybridized in one plane, and then the 90-degree axis would give you the p orbitals, and those are the ones that overlap to give you the pi bonds. And we're still in the valence bond theory. We haven't got out of that territory yet. And this is what the calculated proposed probabilities of finding electrons would be for those orbitals. They would be pointed to the apexes of a equilateral triangle. Okay. And this is an attempt at representing the ethylene molecule. All right, so the green ones are the hybridized orbitals, and the orange ones, the dark orange ones, are the unused p's that overlap to give you the pi bonds. Okay, how about carbon dioxide? Let's take a look at that one. Okay, CO2. All right, we've got valence electrons for carbon, 4. And then 2 times 6 is 12. So we have 16 electrons. Okay, carbon, carbon, oxygen, oxygen. 2, 4, 6. 10 electrons. 2, 4, 6, 8, 10, 12. Did I do that right? 1, 2, 3, 4, 5, 6, 12. 4, 16, yeah. 2, 4, 6, 10 electrons. Okay. 2, 4, 6, 8, 10, 12. All right, I'm doing something wrong. 16, 10 electrons. Oh, see what I did? I got an extra carbon in there. Let's try that again. Carbon, oxygen, oxygen. There we go. That looks much more better. So -4. Now we got 12. 2, 4, 6, 8, 10, 12. There we go. Now we want to make an octet. And we found out earlier that the formal charge is best calculated by putting a double bond on either side. So we take 2 of those and make a bond, 2 of these and make a bond. There we go. So there's your Lewis structure. And we've got 2 groups around that carbon. That's linear. Linear only needs 2 hybridized orbitals. So we use an S and only 1 P. So that means we have a P in this one unused. And this one we have 2 P's unused. That is unused for hybridization. We are going to use them. So we've got this sp hybridized carbon will give us a sigma and a pi, and a sigma and a pi. Now, we've got 2 unused p orbitals on that carbon. What are they going to overlap with? So we got to look at oxygen also. Oxygen has 1, 2, 3 groups around it. It would be sp2 hybridized. That would give it 1 extra p orbital left over. And this one would also, so this one has an unused p like that and an unused p like that. And this one has an unused p there. P, 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 and P. So this side would form the pi bond with these, and this side would form it with those. Kind of messy. But you've got 2 unused P's on the carbon and 1 on the oxygen one side and 1 on the oxygen the other side to overlap and form the pi bonds. And the bond angles are going to be 180 degrees. This is the linear molecule. Now, since we only used 1 P and 1 S, then the energy is going to be somewhere. It's going to be halfway in between the S and the P, because you have only 1 P, 1 S, 50-50. And then the other 2 P's that weren't used are at the same energy level as the originals. And that's what the equations predict for our electron probabilities. And this is trying to show for carbon, the greens are the hybridized orbitals, and the yellows are the hybridized for the oxygens, and then the orange are the unused p orbitals. So in reality, one of those pi orbitals is in the plane of the board, and the other pi orbital is perpendicular to that one. That's the only way that we can justify those overlaps. All right. Let's see. Nitrogen. Okay. Here we go. So if we look at nitrogen, we've got 5 and 5 is 10 electrons, 10 valence electrons. So we have nitrogen, nitrogen, minus 2 is be 8. 2, 4, 6. Let's see. Yeah, 2 times 5 is 10. 2 here, yeah. So we need to be balanced. So we got 2 over there, and we got 2 over here. Right? Okay. So we need an octet. If we take 2 of these, 2, 4, 6, 8, that gives that one an octet. Well, let's take 2 of these, go over here. Now they both have octets. And the best way to draw those lone pairs is out here. 2, 4, 6, 8, 10. 10 electrons. Okay, so that would be the nitrogen molecule. Come on. There we go. Each one is surrounded by 1, two groups. So we would have a linear geometry, electronic geometry with an SP hybridization. So this one is SP hybridized, this one's SP hybridized, which means they each have two unused p orbitals. Right, so we go like this, that. Same over here. And there's your p orbitals. And we would get an overlap for this one pi bond, and we get an overlap for this one. That. And like this. So we have one sigma and two pi's for dinitrogen. This molecule is very, very stable. It can be considered inert. That's why they use it in potato chip bags, right, to keep your oils in your potato chips from going rancid. They just exclude all the oxygen by filling it with nitrogen. So when you see the bags on the shelf and you push on them, right, they're kind of stiff and they're filled with nitrogen. So as soon as you open it, oxygen gets in, you start degrading your chips. So you have to eat them fast. That's my excuse anyway. Okay. So we get two pi bonds. Carbon dioxide also had two pi bonds, but one was on one side of carbon and one was on the other side of the carbon. In the dinitrogen, both pi bonds are between the nitrogens. And that's what it would look like. Okay, PCl5 is an example. Let's see, we've covered 2, 3, and 4 groups. PCl5, let's see what it looks like. So this is 7 times 5 is 35. And phosphorus is 5. So we have 40 electrons. And so we put P here, 1, 2, 3, 4, 5. Chlorine, chlorine, chlorine. Okay. 2, 4, 6, 8, 10. And 30 electrons left over. 2, 4, 6. 6 times 5 would be 30. Okay, we've used up all our electrons and they're no lone pairs. So the structure here would be trigonal bipyramidal. Okay. Oh, okay. All right. So how do we, if we tried to hybridize S and P's, we can only get 4 groups out of SP. So how do we hybridize to get 5 equal orbitals? We have to go to the D's. And notice phosphorus is in the 3rd period. The 3rd period is where you introduce D orbitals, right? 2, you can only get S's and P's. 3s, you can get S, P's, and D's. So we're going to take one D orbital, the S, and all 3 P's to give us a trigonal bipyramid. Okay, so it's going to look something like this, right? Square. It's going to have a phosphorus in the middle. It's going to have a chlorine up here, chlorine down here, and a chlorine at each of these. And that will give you DSP3s. Just count them up. 1, 2, 5. 5 groups. And that gives you bond angles of what? Well, let's see. If you have, well, in this case, every position is occupied by an atom. So you have access to all the different types of bond angles available. On the triangle, right, you have bond angles of 120 degrees, right? And from one of these to one of these is exactly 90 degrees. And then from this one to this one is 180 degrees. So you have those 3 possibilities, 90, 120, and 180. Okay? different bond angles. There it is. DsP3 hybridization. And that's an artist's attempt at showing the bonding. Now, chlorine, it's only got one bond, right? With those hybridized orbitals, it doesn't have to hybridize. Whatever its valence electrons are, the p orbitals, right? One p orbital can overlap. Okay, how about xenon tetrafluoride? Right, let's take a look at that one. Xenon fluoride. Okay, this is 8. This is 4 times 7 is 28, which equals 36, right? Okay, xenon in the middle, and we have 4 fluorides. 2, 4, 6, 8, which is 28, right? Okay, 2, 4, 6. 4 times 6 is 24. 4 electrons left over. They have to go on the central atom. Okay, how many groups do we have? 6, right? 6 is octahedral. How do we hybridize to get octahedral? We just continue with this idea, right? How many Ds do we have access to anyway? 5, right? 3 Ps, 5 Ds. So we could just pick up another D. D2sp3. That gives you the hybridization for xenon. And of course, fluorine just overlaps its p orbital. No problem there. Oh, bond angles. All right. So when we draw xenon, a tetrafluoride, we have this square in the center with xenon in the middle. Where do the lone pairs go? The lone pairs go at the apexes for octahedral groups, and the rest is fluorine. Okay, so this is a 90-degree angle. All these are 90 degrees, and that's all we have. Well, let's see. If we use this one and this one, that would be 180. Let's see. Did I put it in there? No, I didn't. I should have put a 180. Because if you go across the square like this, that's 180. But I guess bond angles are adjacent atoms. So if we say these two are adjacent to each other, we can only have a 90-degree angle. There we go. And the hybridization is on the next page, D2sp3s. Yes. We have 6. We need 1 plus 3 is 4, 5, 6. Now, don't ask me why they put the D's first. If you put them in order of energy, it would be sp3d2. But for some reason, they, I don't know, grandfathered in D's first. Not alphabetical, right? Because the S would come after P. Maybe it's just rolls better off the tongue. All right. And with these shapes have been confirmed experimentally. We mentioned that for the last chapter. Okay. There's what the hybridized orbitals would look like. And there's this table right there. All right. Okay, we're going to throw a hydrogen cyanide at us. I used to work with a man who was for the USDA. He was a technician for the lab, and he was a lepidopterist. You know what that is? They collect butterflies and moths. So he had a huge collection. He'd bring in these trays, and they'd have his moths would be there with their genus and species and where they were caught and when they were caught. and we ooh and ah at them. But he had to have a kill jar. He put them in the jar, and there'd be something in there that would kill them. So what he did was he took, I think it was potassium cyanide pellets, put them in the bottom of the jar, and maybe put a piece of gauze on them, and then covered them with plaster Paris, about that thick. And it was just thick enough to keep the cyanide pellets from being messed up, but the gas would be evolved, and the cyanide would kill the insect. You just put them in there, close the jar, and take them out in about an hour, and they'd be dead. So this is the molecule they want us to draw. Okay, we got 1 electron here, got 4 there, and 5 there. So we have 10 electrons. So we have carbon in the middle, nitrogen, hydrogen. We've drawn this before, I think. This is -4 would be 6, 2, 4, 6. We don't need to put any on this side. Now we need an octet for carbon. So we do that one and that. This will be the Lewis structure. The carbon would be sp hybridized, 1, 2. The nitrogen would be sp hybridized. And since they're sp hybridized, both of them, you've got 2 unused p orbitals on this side, 2 unused on this side. Those p orbitals overlap. A p orbital from that one give you this pi bond, and p orbitals, the other p orbital will give you the other pi bond. And it would be a linear molecule. sp hybridized. There's the sigma, there's another sigma, there's a pi, and there's a pi. Okay. Now, if you want a list status, some of these we've already done. Ammonia, determine the bond angle and the hybridization. Okay, we know ammonia is sp3 with a bond angle of 109.5, nominally speaking. We know it's a little bit less. Okay, now which direction are we going? SO2? Yeah, SO2. So let's do the SO2. So sulfur and oxygen are from the same group, so they have the same number of valence electrons. 3 times 6 is 18. We have an S, oxygen, oxygen, 2, 4 from 18 equals 14. 2, 4, 6, 8, 10, 12, and 14. There. Is that right? 3 times 6 is 18. It's 4. 4, 6, 8, 10, 12, 14. That's right. Okay, we need an octet. We need an octet from that sulfur. So how do we get it? Well, we can't use these 2 electrons because that won't get us anywhere. We have to use 2 from one side or 2 from the other. So that's 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Now we know that we would resonate this one with another structure where the double bond is on the other side. Okay, this has 1, 2, 3 groups, right? Which means trigonal planar. So that means this sulfur, that sulfur has to be, does it say hybridization of the central atom? The central atom is sp2 hybridized, and the bond angles are 120 degrees. Now, do we have to hybridize the oxygens? Yeah. This one would be 1, 2, 3 would be sp2 hybridized, but this one is 4, so it'd be sp3 hybridized. But it would resonate with another molecule where it would be flipped on the other side. But that wasn't the question, so we don't have to worry about it. Okay. Let's see. There it is. Next one is, they're going across, I think, krypton difluoride. So we have 8 here, and 2 times 7 is 14. So we have 22 electrons. Krypton in the middle, fluorine, fluorine. So it's 2, 4 would be 18, right? 2, 4, 6, 8, 10, 12. Minus 12 is 6. So we have 2, 4, 6. So this is 1, 2, 3, 4, 5 groups around that krypton, which means what? It's 5. D, S, P, 3. 3, 4, 5. Now, and the structure would be trigonal bipyramid, right? So we know that the trigonal bipyramid is going to look like this with krypton in the middle, right? Where do the fluorines go? They go up here, down here. So the lone pairs go on the triangle. That means the molecule is linear and the only bond angle is 180 degrees. Okay? All right. So that's what we should get with the next one. Yep. And it's nonpolar. Just threw that in for extra. CO2, we already did that one. All right, CO2 is, let's see, carbon in the middle with only 2 groups is sp hybridized, and the bond angle is 180 degrees. Okay, and then ICl5, iodine pentachloride. Okay, so that's 6 times 7 is 35. 35 valence electrons. And we have an iodine in the middle. 1, 2, 3, 4, 5 chlorines. Okay, 2, 4, 6, 8, 10. Equals 25 electrons. Okay, 2, 4, 6 times 5. 5 times. Wait a minute. Did I do that right? 6 times 7 is 35. Yeah? Okay. 5, 2, 4, 6, 8, 10. Okay. 25. 2, 4, 6. 6 times 5 is 30. Okay, I did something wrong. Oh. 6 times 7 is 42. Right? Okay. So that's 32. Now we're talking. So if we put 6 around each chlorine to get our octet, so 5 times 6 is 30. There we go. We have 2 electrons. Go around the central one. Now we have 1, 2, 3, 4, 5, 6 groups, which means it's octahedral. D2sp3. Now, if it's octahedral, where does that lone pair go? The lone pair goes on a square. So if we draw it like this, then you're going to have a lone pair there. You're going to have a chlorine here, chlorine there, chlorine there. And you're going to have an iodine in the middle, and a chlorine up here, and a chlorine down there. Okay. So what bond angles do we have? Well, we have 180, and we have, that would be 90 degrees, and this would be 90 degrees. So it's 90 and 180 are the only possibilities. I'd left out 180. I would have put that one in. Should have put that one in. Oh, wait a minute. This is octahedral. Guys have to be watchmen. Right? Octahedral. The lone pairs go up here. I was thinking trigonal bipyramid. They go on the triangle. This one, they go on the apex. So yeah, now there is only 180, 90 degree angles, bond angles. Yeah. Okay. Let's stop for a second, let that soak in. Okay, I'm good. All right. So using the localized model, these are just the steps. You still have to go draw the Lewis structure. The SEPR tells you what the electronic pair geometry is. Specify the hybrid orbitals that give you that. Once you know how many pairs or groups are around the central atom, then you just look here. If there are two groups, SP, SP2, SP3, DSP3, and D2SP3. Really straightforward. Okay, let's look at what's really wrong with the localized electron model. First of all, it assumes incorrectly that the electrons are localized around each atom. That's why we get ourselves into a mess and have to use hybridization or resonance to solve problems. It also does not deal effectively with molecules that have unpaired electrons, free radicals. I think we encountered one of those in the last chapter. It was it NO2 maybe? It had an unused electron, unpaired electron. All right, this model doesn't work well with unpaired electrons. And it doesn't provide a direct information ability to calculate exact energies for the bonds. Right. If this were a split class on, say, Monday, Wednesday, or Tuesday, Thursday, this is where I'd stop and pick it up later. But we're moving on. Okay, now we're going to go historically. This came later. It's still based upon the quantum mechanical equations. But the equations are modified to accommodate a situation where all the electrons in a molecule are shared by every atom in the molecule. It's like chemical communism, right? All the electrons are held in common. The terminology, though, is derived from an earlier concept, the Bohr model, where we had orbitals. Like we were thinking electrons orbited the nucleus like a planet. We've long since moved away from that, but the terminology kind of stuck with us. So when we say orbital, we don't actually mean orbiting around something. Orbitals are just a term that defines a level of division. All right, so when we compare the two, localized electron model versus the molecular orbital model, we find that the LEM relies on atomic orbitals and the mathematical calculations that go with them. Whereas molecular orbitals create a whole new type of orbital out of those atomic orbitals. Once the molecule forms, those atomic orbitals, they disappear and they're replaced by molecular orbitals for the entire molecule. All the atoms are treated quantum mechanically. We're still talking about probabilities and solutions to equations. Right, the localized electron model, obviously the electrons are localized on each atom and they're only shared insofar as they create bonds. Whereas with the molecular orbital model, every electron in every atom, that includes core electrons and valence electrons, are included in the molecular orbital structure. And they're delocalized. When you see that word delocalized, the more delocalized you can make the electrons, the more stable the molecule. Spread those electrons out, decrease their energy. We still have 2 electrons per orbital. So when we calculate a molecular orbital, we can still only have 2 electrons in them. And we follow Hund's rule. In other words, degenerate orbitals can only have 1 electron first until they're all filled. So if we had, let's say just 2 molecular orbitals, we'd go like that, and then we could start pairing them up. So we still only have 2 electrons per molecular orbital, just like with the atomic orbitals. And the chi-squared calculations, you get a different chi-square for the localized electron model than you do for the molecular orbital model, but it gives you the same type of information. The energies are quantized. That is, for molecular orbitals, you can only have this energy or this energy, nothing in between. All right. One of the main rules in molecular orbitals is when you bring atoms together into a molecule, the number of molecular orbitals that come out of that calculation are exactly the same as the number of atomic orbitals that went in. So if each of the atoms put together, you have, say, 6 atomic orbitals, then the molecule is going to have 6 molecular orbitals come out of it. It's a conservation thing. We conserve orbitals. Now, the way we do that is we create one type of orbital called the bonding orbital and another type at a higher energy level called the anti-bonding orbital. And I'll show you a picture. I'll draw an energy diagram here in a minute. That will hopefully make that a little clearer. This can get really complex really fast. And it can get so complex that you can't do the calculations by hand. You need a computer. So we're just scratching the surface. Now, we're going to discuss the production when the molecular orbitals are produced by combining atomic orbitals. We're going to discuss those in terms of interference, constructive versus destructive interference, and that's coming. We still say if the bond is on axis, it's a sigma molecular orbital, just like we said with the bonds for the localized electron model. And then if we have any others, they're pi molecular orbitals. So we still use that terminology.
Waves can overlap. When that happens, the highs and the lows can build upon each other. Or they can align in such a way that they balance each other out. When they build upon each other, this is called constructive interference. When they balance each other out, this is called destructive interference. Let's look at what happens step by step when 2 waves travel through each other. Here's a moment when 2 highs overlap. This results in a combined high that's much higher. This is constructive interference. Now, here's a moment where all the highs are perfectly overlapping all the lows. We see a cancellation of the wave amplitudes. This is a moment of destructive interference. If you took a snapshot photo, you might think that nothing is happening. Change that to a video, and you'd see otherwise. In the next moment, you've got a case where the 2 lows are now overlapping. This results in a combined low that's much lower. Once again, we have constructive interference. So, constructive and destructive interference never occur at the same time. Instead, they alternate, one after the other. And then the 2 waves continue on their merry way, having traveled right through each other, amazingly unaltered. Check this out. A wave can bounce off of a rigid structure. Let's add a second wave. Cool. Let's add a second wall and try to confine a single wave. Aha. What we've got here is called a standing wave. Notice that to have a standing wave, the dimensions have to be just right, typically some multiple of the wave's wavelength. A musical instrument, such as a guitar or a flute, is engineered just right to accommodate standing waves, vibrating within the instrument, producing beautiful sounds. That's good energy.
All right, so that's a very simplified description of constructive versus destructive interference. You have to realize that when we're talking about molecules, you're in 3 dimensions. So it's much more complicated, mathematically speaking also. All right. When these waveforms overlap one another, we call that superposition. And what they do to one another is called interference. Constructive versus destructive interference. And I imagine that there can be partial constructive or partial destructive when the waves overlap. Those are very simplified versions where you have 100% construction or 100% destructive interference. But I would bet that you have gradations in between. You can form very complex patterns with these overlapping waves. In fact, when you listen to the radio, they say someone's talking into this microphone, right? And they talk with a wave here. It's converted into an electrical signal, and that electrical signal is superposed on a carrier wave that might be like this. So you get something that, who knows what it looks like. Then when it gets to the other end, we destructively interfere with this same carrier wave, only we shift it so that it will cancel out this part of the wave and it leaves behind this one. And then it comes up and there you have a speaker. So that's how radio works. Television works the same way, only it's more complicated. We call it multiplexing. And that's how you can get a lot of data transferred over a coaxial cable or a fiber optic cable. You have several channels, right? Call it bandwidth. Lots of channels in that bandwidth that are sending information. And each one has a carrier wave, a different carrier wave. So at the other end, you just superpose the correct carrier to destroy it and produce the data stream for each one of those channels. That's one way. The other way is to send them serially, right? On just a single shot, and you have information coming at this and the information behind it, and there's a separator in it, and the electronics know when to stop and record that information. So there are a number of ways you can do it. This is one possibility. You probably don't remember back when we had these parallel cables. They were cable ribbons, and they had individual conductors in them. And you plugged them in the back of your computer. The connector was about that wide, and you had this big ribbon coming off with like 8 or 16 different wires. And each one of those wires carried a signal, and it went from here to there, and on the other end, it took the signals from each one of those and recombined them. So there are a number of ways to do it. All right, so let's look at molecules and the constructive and destructive interference possibilities. when you combine two hydrogen atoms, let's draw the energy diagram here. So that's the energy level increasing in that direction. And this is an individual hydrogen atom, and this is an individual hydrogen atom. This is the combined. So it's going to have 2 electrons with it. So on this side, we have a 1s atomic orbital with a single electron in it. And on this side, we have a 1s with a single electron in it. All right. When we combine those into this molecule, now we have 2 atomic orbitals. We have to have 2 molecular orbitals in the molecule. So we get one bonding at lower energy and one anti-bonding at higher energy. So this is going to be a sigma derived from the 1s orbital. This is going to be a sigma star derived from the 1s orbital. So there's your bonding and there's your anti-bonding. That's really not a good scale. They're supposed to be equally spaced above and below. Now this slide tries to show you what the electron density would look like. The bonding orbital places most of the density between the atoms. And the anti-bonding orbital actually puts a node between the atoms. But the anti-bonding orbital is going to be higher than the bonding orbital. That's bugging me. Let me make it look better. Halfway in between. So sometimes we draw tie lines to show where they came from. That. Now, these disappear and these are left behind when we form the molecule. We follow the same rules, the Pauli exclusion principle and Hund's rule. So Aufbau principle, we start with the lowest energy and start filling up. So we have 2 electrons. One can go here and the other can go there. Okay, so both electrons go into a bonding orbital. That's good if you want to form a bond. You have more in the bonding than you do the anti-bonding. Oh, I didn't realize I had a picture. Okay, that's what it would look like. And this is the simplest description of a molecular orbital, the easiest to understand, because you've only got 1 orbital each. It can get really complex really quick. Okay. This molecular orbital model produces these electron distributions and can calculate their energies. And they agree with all the basic ideas we have about bonding and the calculations that we can produce and determine in the laboratory. So the molecular orbital theory is much closer to reality, so to speak, than any of the other theories. It gives you more information. I think that sigma 1s is in there out of order. All right. And the convention is you form the sigmas first because you always have 1 sigma and then the pi's come next. So we could have, in other molecules, you would have a sigma out of the 1s. Then you would have a sigma star out of the 1s. Then if you combine p's, you've got 3 on each side. So you're going to combine to get a sigma from the p's, a sigma and a sigma star from the p's. Then you're going to get 2 pi's. One pair bonding and 1 pair anti-bonding. So that gives you go 3 plus 3 is 6. You get 1, 2, 3, 4, 5, 6. I'll show you that in just a second. We'll use a more complicated situation. All right. Fluorine, for example. Let's see. This is a shorthand way of showing fluorine. So let's draw fluorine in our energy diagram. See if I can squeeze that much information in here. Normally what we do is we only, for convenience, we put in only the valence shells. So we start with 2 because fluorine is in the second period. But in this diagram, in this method, we've also included the 1s's. So if we did that down here, we'd have fluorine here, and then difluorine there. And let's see, we have, 9? We have 9 electrons, and 18 here. So if we start down here with the 1s's on either side, it would be like hydrogen. Only these would be much lower energy than hydrogen because you have a higher nuclear charge for fluorine, and it would pull that 1s molecular orbital closer to the nucleus. It would be much lower energy. So if we do like this, that, then we would have a sigma star from the 1s and a sigma bonding from the 1s. That, okay? Then we would have a 2s right here. Okay, and this would produce a sigma from the 2s and a sigma star from the 2s. Okay, then we would have 2 p's, and we'd have 3 of them. 1, 2, 3. And 1, 2, 3. Okay. This would also give us a sigma, but formed from 2p. And then at the highest one would be sigma star, the 2p. Then we would get an intermediate because we took one of these, we took these 2 and formed this one and that one. Then we took these 2 and these 2, 4 of them, and we formed these 4 bonds. These would be pi from the 2 p's, and these would be pi star from the 2 p's. Okay. So there we have our, let's see if we have enough of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 molecular orbitals. Okay. Now, how many electrons do we have over here? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 and 9 is 18. 18. So we start from the lowest energy. 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we used up these molecular orbitals, and there's nothing in that one. Okay? All right. Now, the shorthand version, see, I'm going to have to erase some of this, simply takes these orbitals and turns them 90 degrees and puts the lowest on the left, just like we did for each electronic structures for atoms. So that means we would have a sigma 1s, a sigma star 1s, a sigma 2s, and a sigma star 2s. That takes us up to here. Then we would have a sigma 2p. We'd have a pi 2p. Then we'd have a pi star 2p and a sigma star 2p. And if you write it that way, then that saves you a whole lot of trouble. As long as you know that the order is this in energy. And then we just fill in the electrons, right? Each sigma can have 2, 2, 4, 6, 8, 10. These can have 4 because there are 2 of them, right? So we can have 4 there, 2, 4, 6, 8, 10, 14, and then 4 would be 18, right? And we wouldn't need that last one. Okay? All right. All right. Usually we leave out the non-valent, we only use the valence shells. Now, what can we do with this information? We can calculate what's called a bond order. A bond order is analogous to the types of bonds that you have. So if we have a bond order of 1, that's a single bond. If we have a bond order of 2, that's a double bond. Bond order of 3 is a triple bond. Only bond orders can be fractional, whereas single, double, and triple bonds can only be whole number multiples. So how do you calculate a bond order? First, you need the number of bonding electrons. So we have 2, 4, 6, 10. And you subtract the number of antibonding, 2, 4, 8. Then you divide by 2 because there are 2 electrons in each orbital. So that's 2 divided by 2, right? 1. That's a bond order of 1. So what we're saying is between those fluorine atoms, there's a single bond. And that's exactly what we observe. While we're here, what if we said, okay, I want to form an F2 minus molecule, right? Have an extra electron. Where does that electron go? Well, it's full here, so we have to put it there, right? So that means we would have 11 minus 8 divided by 2, which would be 1/2. What does that mean? That means we have weakened the bond. Okay. If we did this, instead of adding 1 there, we'd subtract 1 from here. That would be 3. So now, instead of that, actually, I should have left that alone. 2, 4, 6, 10. 10. We subtract 1 from this side. That's 7, right? 3 divided by 2 is 3/2, or 1/2. By making that ion, we have strengthened the bond. Okay. That calculated for hydrogen, 2 minus 0 divided by 2 is 1. And that says there's a single bond between the hydrogen atoms, and that's what we observe. If we make the negative ion for hydrogen, we have to add the electron to an anti-bonding orbital, which reduces the bonding order by half. Oh, we got a video. Here we go. This is kind of long, but it's a good explanation.
Today we're going to discuss molecular orbitals. But before we can get to molecular orbitals, we have to first consider atomic orbitals, something that hopefully we're all pretty familiar with. So let's start with hydrogen. Here I have 2 isolated hydrogen atoms. And we know that each isolated hydrogen atom should have 1 electron located in the 1s subshell when in its ground state. And of course, we know that these electrons don't move in perfect circles around the nucleus as I've depicted them here, but they do define a region of space defined by a sphere. But when 2 atomic orbitals combine to help form a chemical bond, something special happens. In the case of hydrogens, those 2 1s subshells combine and form a region of space known as a sigma molecular orbital. And a sigma molecular orbital is a region of space where the electrons live generally in between the 2 hydrogen nuclei, screening the repulsive force that their positive charges have on one another. So they stabilize, keeping these 2 nuclei close together. This is a bonding molecular orbital. But there's one rule that we haven't yet considered, and that is that the number of atomic orbitals going into an MO system must be equal to the number of molecular orbitals that that MO system contains. So our molecular orbital system is not yet complete in this depiction. We have 1 more molecular orbital that forms. That new molecular orbital that forms is called a sigma star molecular orbital. And it looks quite different from the sigma MO, doesn't it? if there were electrons inside of this sigma star molecular orbital, they would spend most of their time outside of the two nuclei, not screening their positive charge repulsions, and therefore would actually make the system very, very unstable. So let's think about what that means in terms of how hydrogen atoms come together to form a bond. In order to fully understand the molecular orbitals of an H2 molecule, we have to plot them in terms of energy. So here in this depiction, I've shown the two atomic orbitals here as these lines in blue. That will be our non-bonding energy. Unless there's an energetic benefit to forming molecular orbitals, these two atoms aren't going to get together and do that. So bonding molecular orbitals will be lower in energy, and antibonding orbitals will be higher in energy than this purple line that I've drawn. So let's combine these two different atomic orbitals into molecular orbitals and see what happens. When this happens, we always get a combination that is sort of centric around that non-bonding energy. In this case, we formed two new molecular orbitals from our two atomic orbitals. One is the sigma, one is the sigma star. Next, we have to populate our new molecular orbital system with the electrons that we know the atoms are bringing to the party. In this case, one from each. When we do this, notice that those electrons go into a lower energy orbital overall, and this lowers the overall energy of the entire system. So this energetic benefit that comes from forming and populating molecular orbitals leads us to the prediction that hydrogen will form a bond to another hydrogen. But beyond that, we can actually calculate exactly how many bonds will form. We call this the bond order, and it's calculated quite simply, using the number of bonding electrons minus the number of antibonding electrons, divided, of course, by 2, because we know it takes 2 electrons to form a chemical bond. In our example here of hydrogen, we have 2 bonding electrons, and we have no antibonding electrons. Consequently, our equation tells us that we expect 2 hydrogen atoms to get together and form a chemical bond with an order of 1. In other words, a hydrogen molecule should have a single bond. And that is, in fact, exactly what we see. Now let's move on to the next element on the periodic table, helium. Now I've put molecular orbitals here in quotations because, as we're about to discover, there really is no such thing as a helium-2 molecule. But to prove it, we need to use our energy diagram and combine the 2 atomic orbitals of helium atoms to find out what the energetics of bonding would be if it were to happen. So let's go ahead and do that now. We combine them into a system with a sigma and sigma star molecular orbital, and then we populate that system. Now, in this case, I have 2 electrons that can fill the sigma bonding molecular orbital, lowering the overall energy. But I still have 2 more electrons that have to go into this new molecular orbital system. And they have no choice but to go up in energy and populate the sigma star. The consequence of this is that there's no real energetic benefit to bonding, so 2 helium atoms have no real incentive to get together and form an He2 molecule. And in fact, that's exactly what we see. When we calculate the bond order, we find that 2 bonding electrons and 2 antibonding electrons leads to a situation where we predict a bond order of 0. In other words, we don't predict a bond at all. And when we study helium in the laboratory, that's exactly what we find. Helium exists as isolated atoms. Now let's expand our discussion and consider the molecular orbitals of elements from the second row of the periodic table. We're going to begin with fluorine. Now, fluorine, we know, has available p orbitals because it's in the second row of the periodic table. So atoms of fluorine have 3 different 2p orbitals to donate to forming new chemical bonds. And within those orbitals, we know each has 5 electrons. So let's think about, first, how those atomic orbitals combine, and second, how those electrons can populate the new system energetically to make something that's beneficial. When we combine p orbitals, we find that we have a system that looks a bit different, don't we? In this case, a grand total of 6 atomic orbitals must combine to form a grand total of 6 molecular orbitals. Now, the lowest and highest in energy of these correspond to the in-phase and out-of-phase overlap directly along the nuclear axis. Those we would call the sigma and sigma star molecular orbitals. But we have some new players here. Those are the orbitals that result from the side-to-side overlap of p orbitals that we call pi and pi star MOs. So we have to figure out exactly where the electrons will go in this system and whether or not there's a real energetic benefit to putting them there, and that will help us determine whether or not fluorine will make a bond. Let's do that now. When we put all of our bonding electrons in, we notice that 6 total electrons go into bonding molecular orbitals. This is a tremendous energetic benefit. The sigma and the pi bonding MOs are completely filled. But fluorine has extra electrons, and they have to go somewhere. And the next best available option is to place them into the pi star molecular orbitals. These are antibonding, so the energy comes back up somewhat. However, notice that overall, we still have a system in which, on average, our electrons are in lower energy locations when they're in the molecular orbital system. There's a little bit of an energetic benefit here. And our calculation for bond order lets us know that when you have a grand total of 6 bonding electrons and a total of 4 antibonding electrons, you would expect that species to form a single bond. And in fact, when we study fluorine in the laboratory, that's exactly what we find. A molecule with a single bond. Now let's move on to something a little bit more complicated. Here's another second row element, nitrogen. Nitrogen also has 2 p atomic orbitals available, but in this case only 3 electrons in each. So let's combine those and form a new molecular orbital system. You might notice something changed here, right? Notice that the sigma molecular orbital is actually higher in energy than the pi. And this is an interesting phenomenon. It's caused by something called sigma pi mixing. And we won't go into great detail into it here, but I wanted to point it out because this is how you'll probably see it in your textbooks. Nonetheless, when we use the electrons from nitrogen's 2p orbitals to populate this new MO system, notice that they all go into bonding MOs. And better than that, there's nothing left. There are no extra electrons to fill in those antibonding MOs and counterbalance the energetic benefits. So this is a tremendously energetically beneficial arrangement. When we calculate the bond order of an N2 molecule, we find that having 6 bonding electrons and absolutely no antibonding electrons, we expect a nitrogen molecule to have a triple bond. This is a very strong bond, which makes nitrogen gas almost completely inert. And again, when we go into the lab and study nitrogen, that's exactly what we see. A diatomic molecule with a triple bond. Now let's consider one more element from the second row of the periodic table. This time we'll consider oxygen. And I promise, I'm not wasting your time here. We're going to see something new. Now, just like any other second row element, oxygens have available 2p subshells. And we know from their electron configurations that each oxygen contains 4 electrons in those 2p subshells. So let's combine them to form some molecular orbitals. When we do this, we don't see any real surprises here. Sigma, sigma star, pi, and pi star molecular orbitals form. 6 atomic orbitals in, 6 molecular orbitals out. And if we fill them from the lowest energy to the highest, we notice that 6 of these electrons will go into bonding molecular orbitals, giving us a nice energetic benefit. But there are still 2 remaining electrons. And here's our new question. They clearly should go to the pi star MO, but should both electrons go into one, or should they each take a separate molecular orbital for themselves? The answer to the question is rooted in Hund's rule and the Pauli exclusion principle. electrons will try to spread out and maximize spin. So, when they populate this new molecular orbital, they do so like this, raising the overall energy a little bit, right? Not enough to completely counteract all of those bonding electrons, so there will be a bond formed here. O2 molecules do exist. But even more importantly than that possibly is this. Notice that there are unpaired electrons in this molecule. And that means that our new oxygen molecule is paramagnetic. Liquid oxygen can be trapped within the confines of a powerful magnet. You may have seen this demonstration done before. And of course, just as before, our prediction is correct. If we calculate the total bond order of oxygen using 6 bonding electrons and 2 antibonding electrons, we find that the 6 and the 2 leads us to a calculated bond order of 2. Oxygen exists as a diatomic molecule with a double bond. So I hope that by now you're beginning to appreciate the power of molecular orbital theory. It not only confirms so many of the other topics we've already discussed on bonding, but it allows us to explain completely new properties that all of our other theories couldn't, things like the paramagnetism of oxygen. This is just the beginning of molecular orbital theory. You may want to consider in the future things like molecules that consist of 2 atoms that are not the same, or molecules that consist of even more than 2 atoms. There's much, much more to explore. But for this lecture, we're done. Thanks for watching.
So far we've only studied homonuclear diatomic molecules. That is, same elements in a pair of elements, in a pair of atoms bonded together. Those are the easiest ones to explain. The discussion there was at the very end, the narrator said that oxygen is paramagnetic. Magnetic means para is a Greek prefix that means alongside of or with. So paramagnetic is, it likes magnetic fields. It's drawn into the magnetic field. And that happens whenever you have unpaired electrons in the molecular structure, which is characteristic of oxygen. It has 2 unpaired electrons. Now, the thing about that is unique for molecular orbital theory is that the valence bond theory couldn't predict that. Valence bond theory would predict that it would be diamagnetic. And when we say diamagnetic, dia means opposite, like diameter, like from one opposite end to the other, diameter of a circle, or diametrically opposed means against. So anything that's diamagnetic opposes a magnetic field. It'll be repelled by the magnetic field, and that occurs when all the electrons in the molecular structure are paired. There are no unpaired electrons. You only need 1 unpaired electron to get paramagnetism. 2 unpaired electrons will give you a stronger paramagnetism, and consequently 3 or 4 unpaired will give you, I don't know about 4 or 3. 2 is as much as I can think of. All right. It can be measured. So this is a diagram of the type of situation you would have a balance that can measure, and you lower your sample into a magnetic field and then measure whether it's repelled or attracted using a balance. It probably doesn't look exactly like that, but that's the idea. There's one of those huge, have you ever seen one of these horseshoe magnets? They're monsters. And if you've got a pacemaker, I wouldn't get close to one. No, that holds the oxygen in that magnetic field, at least until the liquid evaporates.
It's Professor Dave. Let's revisit molecular orbital theory.
He knows a lot about the science stuff. Professor Dave explains.
We've learned a bit about molecular orbital theory and the ways in which it differs from valence bond theory. But let's expand on this knowledge now so that we can understand a phenomenon called sp mixing. But before we get into that, let's take some time to review the basics. First, let's compare valence bond theory and molecular orbital theory. Valence bond theory considers covalent bonds as being localized between a pair of atoms, resulting from the overlap of atomic orbitals or hybrid atomic orbitals. This overlap results in sigma or pi bonds, and we can use this theory to predict molecular shape. However, there are simple molecules that do not conform to this theory, like the diatomic oxygen molecule. Given this Lewis structure, where each oxygen atom has a full octet, we would expect oxygen to be diamagnetic and weakly repel a magnetic field. However, it does in fact exhibit paramagnetism, as liquid oxygen is attracted to a magnetic field. To explain this, we have to turn to molecular orbital theory, which differs from valence bond theory in that electrons are considered delocalized throughout the molecule, and atomic orbitals combine to form molecular orbitals, which are also delocalized throughout the molecule. These can be sigma and pi bonding orbitals, or sigma star and pi star anti-bonding orbitals. This theory ends up being better equipped to predict the arrangement of electrons in a molecule in certain situations. This is due to a process called the linear combination of atomic orbitals. In the modern physics course, we talked a little bit about the wave function, and molecular orbitals are combinations of atomic orbital wave functions. Just the way the wave function describes the behavior of an electron within an atom, molecular orbitals describe the behavior of an electron within a molecule. And just like atomic orbitals, they are filled when they contain two electrons of opposite spin. This theory requires that we strongly consider the wave nature of the electron. In the classical physics series, we talked a lot about waves and interference patterns. So to get the full picture of wave behavior in order to better understand molecular orbitals, check out this tutorial now. Otherwise, we simply need to understand that when two atomic orbital wave functions are combined, like these two s orbitals, there can be constructive interference, where the peaks line up with the other peaks. This causes the amplitude to increase, which results in a bonding molecular orbital, like the sigma s orbital. Most of the electron density is between the nuclei, which strengthens the bond. There can also be destructive interference, where the peaks line up with troughs. This causes the amplitude to drop to zero, resulting in an anti-bonding orbital, like this sigma s star orbital. Here, there is a node between the nuclei, which weakens the bond. The bonding orbital is of lower energy and will thus be filled before the anti-bonding orbital. For this to make more sense, we simply need to understand that these images of waves are just two-dimensional analogies to help us visualize the type of overlap. Electrons are three-dimensional objects, so the waves are in 3 dimensions, and constructive interference thus results in regions of greater electron density, while destructive interference results in regions of no electron density, which are depicted by these bonding and anti-bonding orbitals. We can do the same thing with p orbitals, utilizing direct overlap, which will yield sigma px and sigma px star molecular orbitals, or lateral overlap, yielding pi and pi star molecular orbitals from the overlap of py and pz atomic orbitals. Orbital number is always conserved, which is why the linear combination of 2 atomic orbitals will always result in 2 molecular orbitals, one bonding and the other anti-bonding. We can depict these linear combinations with molecular orbital diagrams, as we have seen. The dashed lines show how the atomic orbitals on the sides combine to form the molecular orbitals in the middle, such as we see here for hydrogen, with two 1s orbitals combining to form one sigma s orbital and one sigma s star orbital. If we go up to the electrons in the n equals 2 shell, we can see the 2s orbitals combining in precisely the same way, and then the 2p orbitals combining as follows, with the sigma bonding orbital and then pi bonding orbitals, followed by the corresponding anti-bonding orbitals. The good news is that these orbitals are still filled according to the Aufbau principle and Hund's rule, like we already know. This means that we fill them from lower energy to higher, according to Aufbau, and we will put one electron in each orbital for a set of degenerate orbitals before doubling them up, according to Hund. We've already learned in a previous tutorial how to fill in these MO diagrams for certain diatomic molecules, like O2, and how to use them to calculate bond order. Here's that diagram one more time, along with the calculation for bond order, with 10 bonding electrons, including the sigma 1s bonding electrons, and 6 anti-bonding electrons, including the sigma 1s star anti-bonding electrons. 10 minus 6 is 4, and 4 over 2 is 2. This explains the double bond in diatomic oxygen. But we also get an explanation for the paramagnetism of the oxygen molecule. We have two unpaired electrons in these antibonding orbitals, which does predict paramagnetism for this molecule. This is an example of the success of molecular orbital theory, as no other theory can account for this behavior. Now that we are up to speed, let's go over one other thing. The molecular orbitals that result from the combination of the 2p orbitals exhibit this order in O2, but this will change for other homonuclear diatomic molecules. Let's look at this diagram, which depicts the relevant orbital energies for all the potential homonuclear diatomic molecules in the second period, from lithium to neon. As we go to the right in the period, effective nuclear charge increases, so the atomic radii contract, and the orbitals get lower in energy. On the left, the pi 2p bonding orbitals are lower in energy than the sigma 2p bonding orbital, but on the right, the sigma 2p bonding orbital dips below and thus will be filled first. This discrepancy is due to a phenomenon called sp mixing, which influences the energies of these molecular orbitals. This happens when the sigma s and sigma p wave functions combine in such a way that the sigma s orbital becomes more stable and the sigma p orbital becomes less stable. As a result, we see the sigma s and sigma s star orbitals going lower in energy and the sigma p and sigma p star going up in energy. So much so that the sigma p orbital now sits above the pi p orbitals. Molecules like O2 and F2 have negligible sp mixing because the 2p orbitals in those atoms have some paired electrons. This raises the energy of the 2p orbitals, making them too dissimilar to the energy of the 2s orbital to allow mixing to occur. But going to the left on the period, where p orbitals have unpaired electrons or are vacant, the 2p and 2s orbitals are of similar enough energies that sp mixing will be prevalent and the order of the molecular orbitals will switch. While this is an interesting phenomenon, if we are only using these diagrams to calculate bond order, it won't matter because it is just the order of bonding orbitals that is being rearranged, so it won't affect a bond order calculation. Nevertheless, we have hopefully reached a more sophisticated understanding of molecular orbitals. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. So there's that diagram that he showed us. And this is simply the order of orbitals And this diagram is included in your review document at the back, which means that it'll also be on the exam. And he gave a pretty good explanation for why you get the mixing. But as a practical matter, if you want to know in the 2P period, which ones experience SP mixing and which ones don't, the dividing line is between nitrogen and oxygen. So oxygen and fluorine do not experience mixing. That means the sigma comes before lower energy than the pi's. And the nitrogen and to the left, you get the pi's at a lower energy than the sigmas. Okay. This is another possibility, another diagram, and it shows that the dioxygen and difluorine experience no mixing. So we have the sigma star, followed by the sigma 2p and the pi 2p, and then the pi star and the sigma star for oxygen and difluorine. And then the nitrogen, carbon, and boron to the left are also populated with their electrons. So this way you can tell from the pairing and unpairing of electrons which ones are paramagnetic and which ones are diamagnetic. And they're also identified in the diagram as one or the other. The bond order is calculated, and the observed bond energy, the experimentally observed bond energy, is given. And the bond lengths also. So as you increase the bond order, you should decrease the bond length and increase the bond energy. And that's what we see. So there shows that's the swapping of those sigma and pi 2p orbitals. Okay. Sometimes they're called, in fact, in that earlier video, it was identified as sigma pi mixing rather than SP mixing. You'll hear it both ways. Okay. Now, we can also introduce the topic of heteronuclear diatomic molecules. Right? So in this case, we have carbon and oxygen bound together. And if it's just carbon and one oxygen, we're talking about carbon monoxide, which means that we should have a triple bond or a bond order of 3 if we do the calculations. Notice that the carbon is, the atomic orbitals are at higher energy than the oxygen orbitals. And that's simply because carbon is to the left of oxygen. It has a lower nuclear charge. So the orbitals exist at higher energy levels. They're not drawn in by that positive charge like they are with oxygen. So that presents a problem for calculating which ones actually combine to produce the molecular orbitals. So in these cases, since we're not really into actually calculating them, determining them, those would have to be given to you. Exact order of the molecular orbitals. But if we calculate, let's see, are we going to do that? No. We just have one other animation. Oh, it's not shown. So there was there a problem? No, there wasn't a problem. Okay, my copy has the error noted, and in this copy, there's no error. An earlier version for the carbon had, instead of 2s there, it had 1s, and that's an error, but it's since been fixed. If we do the bond order for this one, I should be able to do that pretty quick. So let's see, bonding electrons. Let's see, we have a sigma S 2, 4, 6, 8. So we have 8 bonding electrons, and anti-bonding we have just 2, correct? Yep, just 2. Divided by 2, so this is 6 divided by 2 equals 3. So yeah, carbon monoxide has a triple bond. And it should be diamagnetic because all the electrons are paired. What happens when you combine hydrogen and fluorine? Right? Fluorine has 1s, 2s, and 2p orbitals. And hydrogen has 1s orbital. That's it. That's the only thing that can be combined. So since hydrogen only has one proton, the 1s orbital is very high energy relative to the 2p orbitals of fluorine, which has 9 protons in its nucleus and draws those orbitals in closer. So the combination of orbitals for HF are the 1s for the hydrogen and the 2p for the fluorine. And we get a sigma and a sigma star. Combine those, you get essentially a single bond. Right? 2 minus 0 divided by 2 is 1. And that's what we observe in the molecule. Okay. But notice also, let's go back to that diagram. Notice also the proximity of energies for the sigma bonded electrons in the molecular orbital to the individual atoms. Relative to the energy of the hydrogen, those sigma electrons are closer in energy to the fluorine atomic orbitals, which implies that those electrons are going to, their electron density is going to be drawn closer to the fluorine because of the similarity of the energies. And that's what we observe. We observe a polar molecule with the electron density shifted toward fluorine. In the past, we looked at it in terms of electronegativities, right? The difference between hydrogen and fluorine. But this is another way of explaining it. And actually, this way, you can calculate that distribution, that difference in electron densities that we see here illustrated. There's a sigma bond, all right, but the electrons tend to spend more of their time, or the electron density tends to shift toward the fluorine nucleus. Okay, it just says more of the same right there. Delocalization, I mentioned that earlier. The way we described delocalization in the valence bond theory was with resonance. We had no way of describing this delocalization in actual terms of Lewis structures or bonding structures of any kind. The best we could do was something like, I don't know, like this. Right, the nitrate ion. We sort of implied that there was an intermediate delocalization of the electron structure. But in fact, what we observe and what we can calculate with the molecular orbital theory is the electron density is like that. It's really delocalized over all 3 of those bonds. Here's another example, benzene. Benzene can be drawn. Let's erase this. And when you see organic molecules, they might be drawn this way, like that. And let's see, they're positioning here, 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 and here. This benzene molecule, you'll see it only drawn like that. But in organic chemistry, everywhere you have 2 lines coming together, there's a carbon atom. We don't draw them in because it gets really busy if you do. And then carbons always have 4 bonds, some kind, unless there's special cases. But most of the time, if it's drawn this way, there's 1, 2, 3, and the 4th bond is not written, it's a hydrogen. So we would put a hydrogen on each one of these. Okay? But if we shift this double bond over here and this one, and we just shift them 1 bond over, we can get a resonant structure, right? And that's the way the valence bond theory would depict benzene. But if we draw it to demonstrate a molecular orbital situation where you have delocalized structure, often what we see is we do that. That means that these electrons are delocalized around that six-membered ring in such a way that all the bonds are exactly equal in strength and length. And that can be demonstrated experimentally and mathematically with the molecular orbital theory. Right. If we do the benzene here, using the hybridization model, then that's what we get. And then we would have to overlap p orbitals to get this, p orbitals to get that, p orbitals to get that. But what in fact actually happens is all of those p orbitals delocalize electrons in the ring. And that causes a great deal of energy benefit, a stabilization of the molecule, such that this is a class of aromatics. Aromatics are notoriously stable. Any type of molecule that has this ring structure in it. And there's some other rules that go with it. So if it's aromatic, it is. And if we have rules to go by, we can determine whether it is or isn't. But if it is aromatic, it's very stable. And that's a representation of the overlap of those p orbitals to delocalize the electron structure. Now, what we're introducing here is the localized electron model combined with a molecular orbital model. So it's kind of a, I don't know what you call it. A jerry-rig system. I don't know. And here's your example for the nitrate ion. All right, so resonance structure would be called for if we were in the localized electron model, but in the molecular orbital model, well, that's another way of showing it. This is what it would look like for a representation of the nitrate ion where the delocalization is over all the bonds. And that stabilizes the bonds. Now there's a term for that. I thought I had it in here. Oh, here it is, conjugated. Right, this is an aromatic system. Aromatics always are ring structures. You can also stabilize a series of bonds with conjugation. And in order to get conjugation, a ring, not a ring, but a series of carbon atoms bound together with some whatever else is on them. If you do like this, this, and this, and say, maybe let's put another one over here, then an alternating double and single bond signifies a conjugated system. And the conjugated systems redistribute their electron densities over all of those bonds, and that stabilizes them. It lowers their energy. And you can detect that stabilization with their absorption wavelengths in a spectrometer. So the more of these they have, the more shifted toward the lower energy, or the red wavelengths, or the infrared wavelengths. That's why crawfish and lobsters and crabs have that red colored pigment. Those are carotenoid pigments that have a very extensive conjugated system. They lower the energy of absorbance into the red spectrum. Okay, so one last slide and we'll be done. This is the photoelectron spectroscopy. And the reason this slide is in there is to show that there is laboratory evidence, physical evidence for the molecular orbital theory. The way that we do this is somewhat akin to the photoelectric effect for metals that Einstein published his paper in, when was it? latter part of the 19 teens, but he got a Nobel Prize for it in 21, I think, 1921. But what it says for the photoelectric effect is, say you have a metal and you shine a light here of a particular wavelength energy. So we use our Planck's constant, and right, this is equal to energy. And if it's low enough frequency, then it will eject an electron. If it's exactly the right energy, then it'll free one electron at the surface of the metal, and it has no kinetic energy. It's just free from the metal atoms. If you increase the frequency and give it more energy, then that excess energy, there's a certain amount expended to release it, and then the excess energy gives it kinetic energy. Okay? So that electron now has kinetic energy. It's the excess of what's left over. How much kinetic energy will it have? Well, it depends on how much of the incoming energy is used up to free the electron. Like, if it's an electron that's in one of these outer orbitals, it doesn't take much energy. And then the rest of it gives it a very high kinetic energy. And that can be measured. If it's in one of the inner orbitals, it takes a lot more of that energy to get it loose, then the kinetic energy is lower. So that spectrum is showing you that for the lower energies in the molecular orbital, it takes more energy to get it loose, and we can measure only a small amount of kinetic energy. And when you do the calculations using this, the difference here in energies, and compare those to the measured energies of electrons that are released from the compound using this photoelectric effect, they agree perfectly. So what we're saying is, there's your physical evidence for the molecular orbital theory that agrees and is able to calculate the energies of the electrons. Okay, that's it.